Hello, I'm Matt Rostron. I'm a distinguished engineer, and I also lead the Cloud System Futures team here in Microsoft Research. And it's my great pleasure to be the host for this summit track on the future of the cloud. Now, of course, the cloud is extremely important, and there is a major paradigm shift happening where people are migrating workloads to the cloud. It's a sort of digital transformation of business, society, and human life. And the cloud platforms are just getting bigger and bigger and more pervasive. The speed at which we're deploying the cloud, the speed at which we're deploying data centers, it's just unprecedented. The world runs on the cloud, and it's woven into that basic infrastructure around the world. The quality of that cloud platform is just critical. Reliability, performance, efficiency, security, and of course, sustainability. It's a huge challenge to operate clouds effectively and efficiently. They are massive, distributed, highly complex systems with a matrix of equipment and technology platforms deployed globally. And we're going to hear from the experts from Microsoft and the academic world about what's next for the cloud. We're going to explore the latest technology and what it could mean for people everywhere. So let's take a look at the sessions today. I think one of the most exciting ones for me will be scaling network technologies from data centers to space. Major challenge is how to connect everyone to the internet. And of course, we're seeing a lot of activity at the moment deploying satellites and communication systems to enable this. And Microsoft's Space Connections Initiative is really driving a research agenda on looking at satellites and satellite communications and how deploying edge, AI, and cloud technologies can help drive new breakthroughs in that space. Ranveer Chandra, Managing Director of Research for Industry at Microsoft, will be showing us what lies ahead for this emerging technology. Another one we'll be having is storing data for millennia. Another big challenge for humanity, really, is how to store the huge amount of data that's being generated efficiently and sustainably. And glass is emerging as one of the most promising storage media. We're going to give you an update on Project Silica, the world's first glass-based storage system. And it's really exciting because this project is moving from sort of what I consider science experiments, which started at Southampton University, and is now moving to be a real storage system. And the talk will talk about how we take the technology and how we create storage systems from it. And Jan Stefanovici, Principal Researcher here in Cloud System Futures at Microsoft Research Cambridge, will be giving that talk. The next session is also really interesting. Cloud Intelligence, AI Ops, infusing AI into cloud computing. Qingwei Lin, who is a Senior Principal Research Manager at Microsoft Research Asia, will talk about how AI and ML can help design, build, and operate compute cloud platforms and services at scale efficiently and effectively. This has long been a dream, to be able to have sort of the single person able to run the entire system. And this is how they're getting towards that. And finally, we've got a distinguished panel of cloud experts who we've asked to come together to tell us about emerging computing technologies in academia and industry. We've got top engineers and research leaders from Azure, Office 365, and academia. And we've asked them to tell us what are the next big things we can expect from the cloud. What are those disruptive technologies that are just around the corner? And across all aspects of cloud and systems research, what do they currently see as really exciting? And to kick off today's program, our first session, Computing at the Speed of Light. Now, we're all aware of the end of Moore's Law. That transistor doubling every 2 years, which has yielded so much of that increase in performance that we've just got used to in the last 40, 50 years, has stopped. We need other breakthroughs and innovations to drive efficiency beyond state-of-the-art digital solutions and even the promise of quantum computing. The question we've been asking is, can optical computing help? Can we use light waves or photons for processing data? Microsoft Research Project AIM, or Analog Iterative Machine, is building an optical analog computer to solve the hardest optimization problems at the speed of light. AIM has a completely different architecture to normal systems. It's an asynchronous data flow machine. It uses commodity optical electrical technologies and is low cost and scalable. It offers over 200 times speed up versus state-of-the-art digital hardware. It's a new abstraction for how to encode these problems and has the potential to scale to allow us to efficiently work at scale. It's going to be key, we think, to driving optimization solution in the post-Moore's Law era. So our first speaker, Francesca Parmigiani, a principal researcher at Microsoft Research Cambridge in the UK, will give us an update on AIM and tell us more about that potential to drive this new computing breakthrough.
Hello, I'm Francesca Parmigiani, and today I'm very excited to tell you about computing at the speed of light. We are building an optical computer that can solve a hard optimization problem hundreds of times faster than today's state-of-the-art digital computer and even of quantum computers of the future. And to do so, we use the very same optical technologies that are used today in your smartphone devices. To invent the future, we need to know the past. So let me give you a brief history. Computers were born analog. Charles Babbage and Lady Ada conceptualized computing in the 19th century as analog devices, but it took more than 100 years to see the first physical instantiation of such analog computers in the form of electromechanical differential analyzers. In the 70s, the state-of-the-art in processing of radar signals captured by planes were SARS optical computers. And finally, in the 80s, we have seen the implementation of the first prototyping of optical AI accelerators. All very cool technologies. None of them yet are used today. And this is really because of the exponential gain of digital computers under Moore's law, with the number of transistors per chip area doubling every 2 years for many decades. And the exponential growth allowed computing flexibility without compromising in efficiency. However, as you know, Moore's law has ended, and in order to continue improving computing performance to keep up with the even more increased demands, we have seen a huge effort in building custom dedicated hardware, such as GPU and custom ASIC, for specific domains. And indeed, there is the recognition that it is fine and in fact desirable to compromise flexibility with efficiency for important high-performance workloads. However, the slowing down in digital electronics will eventually hinder those efforts as well, and this has led to lots of interest back in analog solutions, which will allow to gain even more flexibility. However, it is critical to carefully target the applications. And even given a specific application, it's important to understand what is the most efficient and high-performance technology among the vast options of analog computers that can be based on electrons, optics, quantum, and so forth. In this talk, I will convince you that optical computers are extremely promising ones for some specific vertical that I will discuss. However, before moving forward with this, let me first wipe out the popular belief that suggests that electrons are great for computing due to their strong Coulomb interactions, which can enable computing, while photons, they do not interact at all with each other. And so really they are the ideal mean for high capacity communication. And while all these statements are correct, I believe that photons have value for compute too. And in fact, the key observation here is that while photons do not interact with each other, they do interact with the medium they propagate through. And note that what I'm saying here is nothing new really, and in fact these interactions have been extensively used both in communication and in display technologies. For example, to encode data onto light, we may use modulators, and with them we can programmatically control how much light goes through the device. This is like closing on or opening the blind in a room. And if you think about it, you are scaling down the intensity. What we are doing is a multiplication in the optical domain. Similarly, in order to decode the data from light, we can use cameras or photodetectors. How they work is they absorb light and they transform it into electrons. This is again similar to the solar panels that you may have on the roof of your house. The more beam lights they absorb, the more electrons they accumulate. So what we are doing is again addition in the optical domain. And given the potentiality of high parallelization or high throughput in optics, in combination with the opportunity of computing, it is now hopefully intuitive to you to understand how we can efficiently perform large-scale matrix vector multiplication in the optical domain. This operation can be done up to the speed of light with very low transmission losses, even at high bandwidth, at high throughput. And these advantages are combined to the maturity of today's optical ecosystem, for example, with display technology revolution, among others, and can really drive, and in fact have been really driving cost reduction, device miniaturization, and easy integration with electronics. So I believe the time is right to answer the question, is there a new opportunity for optical computers for some specialized but extremely important verticals? We believe that the answer is yes, and the vertical we want to focus on is solving hard optimization problems. So in the rest of the talk, I will cover the optimization space, and then I will deep dive in our specific solver. Let me start with the vertical of optimization problems. Due to the slowing down of Moore's law, as I just described, in the last 20 years or so, we saw lots of effort and money that has been spent to develop custom hardware for optimization problems, which are based on quantum annealers, ASIC, GPUs, and many others. Many different hardware, though, based on the very same abstraction. Some people call it MaxCut, Ising, QUBO, quadratic unconstrained binary optimization, all equivalent. However, it is very hard to map large-scale problems, real problem, on this binary abstraction with any of today's custom hardware. And this is not just me saying that. There was a DARPA call last year where they have highlighted that while they've been funding the research for over 10 years, they realized that this binary abstraction only work for boutique problems and not real ones at interesting scales. Even quantum computers, which are supposed to solve many problems, cannot help us here, as very well analyzed by the Google paper that I'm reporting here. So while there is the consensus that the optimization space is super exciting and valuable, On the technical side, there is the concern that binary abstraction will not map to many real-world problems at interesting scale, and unfortunately, quantum computers have been ruled out. I believe the opportunity comes by combining a superior abstraction beyond the binary one, which I will talk in a second, with the right technology based on commodity optics and the right algorithm. And all of them together will drive optimization in the post-Moore's law era. Indeed, imagine if you would have a solver based on an abstraction that is very efficient and can map to real-world problems at scale. And imagine that it would be hundreds times faster than state-of-the-art digital solver today. What this means is that problems that today take up to 2 hours to be solved in such digital computers could be solved in half a minute with this special solver, real-time optimization. Imagine that such a solver would be extremely accurate at interesting scale of the 10,000, and this could be achieved in a cost-effective manner. I believe that the solver, the optical solver that we are building at Microsoft Research, can tick all these boxes and will enable us to overcome this optimization winter. Let me introduce you our superior abstraction with a canonical example taken from the financial sector, which has been recognized as an extremely important domain in the space. The canonical example is of portfolio optimization with constraints. Given a large batch of stocks, 2,800 in the New York Stock Exchange, the problem here needs to answer what subset of stocks I should invest on in order to maximize my return and minimize my risks. And adding more stocks takes longer and longer to figure it out, so we can see an exponential explosion of the problem. In more detail, for each stock, I need to determine should I invest in that stock, so this is a binary variable, and how much I should invest in it, a continuous variable. In order to minimize risks, we need to model the covariance between each pair stocks, which I'm representing here as a line joining the various variables, the various stocks. So very importantly, these pair stocks correlations needs to happen among all the various stock pairs that we have. So our problems requires mixed variables and quadratic covariance. So we need, we call it QMO abstraction with all-to-all connectivity. Importantly, later on, as we describe the specific hardware we use, these variables, these stocks, need to change very, very quickly because I want to know as quickly as I can which stock I should invest on. On the other hand, the interaction, the covariance between stock pairs, between variables, is fixed for the specific problem. And I believe that QMO with all-to-all connectivity is a very powerful abstraction, as many hard business problems can be formulated as such. So far, I really gave you a very high-level intuition of this abstraction of optimization problem. And what I'm showing you here is how a mathematician would formulate it. So we mechanically transform the original objective function to a quadratic one, our QMO formulation. As you can imagine, this is a very challenging problem, and to solve it, we use a gradient descent method. And because the original function was a quadratic one, the derivative is linear. So to follow the gradient, we need to do lots of matrix vector multiplication. And I hope you have guessed, as I previously told you, we can use optics to do this vector by matrix multiplication extremely efficiently. So let me now show you how we can do this in optics. At the very high level in our solver AIM, analog iterative machine, we encode our variables, our stocks, in the intensity of the light. So maximum intensity, I want to invest in that stock. No intensity, I don't want to invest in that stock. The covariances are encoded in a matrix of modulators. And remember, I told you that those values are constant for a specific problem. What it means is I can store those values on the actual matrix. And finally, the idea of updating my stocks, my variable, is captured by an array of cameras as shown here. So how it works is that I shine each light on a row of the matrix, emulating the fact that each stock wants to interact with all the other stocks in the batch. Basically, what I'm doing are multiplicative operations of the vector by matrix multiplication. And very importantly, those are done in a parallel fashion. Similarly, after that, I'm adding the contribution of all the stock to every individual stock that will then get updated. Again, what I'm doing is the cumulative addition operation of the vector by matrix multiplication. And then the outputs are then fed back to the optical source, and I'm repeating this till the system converges, till I found which stock I should invest on. And there are really three aspects of this architecture that are very important, and I hope you can take home today. The first one is that this is a truly analog machine. The signals are remaining in the analog domain till the solution is spit out. Second, as opposite to Neumann's architecture, there is no separation between compute and memory. The signals are propagating through the solver as I do my computations. And finally, the solution time of the solver is dictated by the path length of my solver, as well as by the bandwidth of the optical devices that we are using. There are lots of technologies out there that we could use for our AIM solver. And the specific optoelectronics technology we use has to be fast, low cost, and very, very importantly, scalable. And we choose commodity optics. In more detail, we use micro-LED arrays as our light source arrays. This is the next big things in display. For our matrix, we use a technology called spatial light modulator. This is a technology very similar to projectors and can be bought off the shelves from several manufacturers. And finally, we use CMOS sensors as our cameras. Remember, exactly the same technology that is in your phone. Let me now move on and tell you about our algorithm. AIM algorithm is an heuristic iterative method based on an advanced gradient descent search. And the graph here shows a typical problem landscape that you may have, and also give you an intuition of how the problems is very complex and how our solver could help in solving it. So what we need to do is finding in this very complex landscape few points with minimal energy. The way we do is, first of all, we perform multiple experiments, which are the dashed lines in the graphs. As you can see, you try from different initial conditions, and in many cases, you end up in local minima. The way that our algorithm pushes away from these local minima are, first of all, we use this advanced gradient descent based on momentum. So we use a sort of velocity to push us away from these local minima. Second, we use an adiabatic process to avoid bad initial condition. So what we do here is we initially squash the landscape. So we start from a very smooth surface, really to be able to search large area. And then in time, we increase the roughness of the landscape till we go back to our original one. This is the actual equation. It is a second-order differential equation characterized by the advanced gradient descent and the adiabatic terms, which I have just explained. We have the nonlinearity to force some of these variables to become binary. And then we have some terms, some parameters, alpha and beta and gamma, that will require a careful choice, as I will describe in the next slides. And really, the beauty of this algorithm is its simplicity that allows efficient, massive parallelization. As I said, we also need to be and find a very smart methodology to carefully choose the parameter in the previous equation to find very good solutions. To quickly evaluate the accuracy of the proposed algorithm at scale, we chose to implement the simulator. We evaluated our algorithm through this simulator on many datasets and benchmarks, and in all cases, our algorithm has been extremely competitive with state-of-the-art algorithm. In this specific case, we have looked at 400 industrially inspired problems, and we compared our AIM algorithm with state-of-the-art digital solver, in this case, the best from simulated annealing and parallel tempering. And the graph here shows the CDF of the reduced inoptimality gap of our solver versus state-of-the-art. As you can see, we are always at least as good as, and in fact, in most of the instances, from 50 to 75%, much better than state-of-the-art algorithm. What is the impact on performance of the parameters? I'm showing here an example for alpha and gamma, but the same discussion holds for beta. So the main challenge here is really to find good value, as initially we are kind of clueless of where we should be. The smart methodology that we use is as follows. So initially we perform a quick sampling of the space of the parameter space, really to build the best profile we possibly can. And then once we have found the good areas, the red area in the image that I'm showing here, we do extensive deep dive searches. So let me finally move on to the last part of the talk and tell you how we implement the solver in hardware. As any analog computer, we need to be extremely mindful of the solver accuracy and the level of precision that we can achieve due to the limited signal-to-noise ratio and dynamic ranges of the optical component that we are going to use. At the very high level, we need to be careful about the minimum power that will hit our photodetectors and the noise of the system. We also need to be very careful on how to scale the solver at 10,000 variables, as we want to do so, in a very compact fashion, as these will have a strong implication of the speed of our solver. So this is at the beginning of this calendar year, we have demonstrated a full working 8-variable optical solver. This is kind of the first of its kind. As you can see, obviously it's based on discrete off-the-shelf components. And this has really been built in order to de-risk the feasibility of the solver and debug its architecture. The graph here shows an example of the energy level of a computationally hard problem at 8 variable that we have evaluated. As you can see, our solver always finds the solution with minimal energy, which is the optimal solution. Importantly, as I previously mentioned, to find good choices of parameter. And so what I'm showing you here is our comparison of heat. We are comparing the heat maps of the parameter space as we sweep the alpha and gamma parameter. We see on the left and the right 2 different problems, and we compare our hardware with our simulators. The red regions is where we find the optimal solution, and the blue region is where we don't find the optimal solution. And as you can see, there is an excellent agreement between the 2 of them. And really, this gives us a great confidence that what we are building is indeed what we have implemented in our simulator. And the fact that the great results that we achieved in the simulator will be confirmed in our hardware with a 100x speed up of improvement. I'm also showing you here the evolution time of these variables from their initial guess, initial condition, to their final stable point. And really here, the takeaway message is that the solution time is proportional to the path length. So obviously, the system, the hardware that I've just described, has a path length of tens of meters. And in order to achieve the targets of solution time that are required, we need to make the system much more compact. And in fact, if you look at the prototype, our first prototype of the GAIN, it kind of looked like a physical lab bench. However, if you think of the first built computers that use vacuum tubes, for example, they were occupying an entire room to process a number of operations comparable to what we are doing with our solver. We know that in the digital world, we transition away from bulky electrical components to today's miniaturized digital devices thanks to this incredible revolution in transistors. And it is easy to envision a similar evolution in the optical domain. And in fact, if we think about our first optical prototype, we can easily envision how we can move to micro LEDs and other miniaturized devices. And for example, in this PCB, custom-made PCB here at the very center, you can see an active area of about 2 millimeters by few millimeters, where you have hundreds of micro LEDs, hundreds of your potential variables or stocks that you need to use for your solver. Similarly, another technology that we can use is what I previously told you, the spatial light modulator. And already off the shelves today, you can have millions of pixels in them. And you should envision each of these pixels as individual optical modulator that we could use for our solver. So a device like the one shown here with an active area of about a few centimeter by few centimeter could potentially process up to 1,000 variables or 1,000 stocks. And these are exactly the technologies that we are using in our second prototyping of our solver. As you can see, we were able to reduce the size from tens of meters to sub-meter in this implementation over here. And really, with this, we were able to demonstrate fast time variable evolution as expected. We are using micro-LEDs, spatial light modulator, and CMOS sensor technology, as I've already explained to you. And obviously, we can further decrease the size of our prototype, going down to the tens of centimeters that is required for our target, moving from off-the-shelf optical components to customized one. And I believe that once we have de-risked 100 variables, which is our next target, we will gain a very good confidence on how to scale from 100 to 10,000, which is our ultimate target. So let me move on how we can scale there. So on the transmitter side, we require 10,000 micro-LEDs because this scales linearly with the number of variables. A similar discussion applies on the receiver side. We require 10,000 CMOS sensors. Ideally, we need 10,000 by 10,000 spatial light modulators. Such a device doesn't exist today. So what we are doing is having an array of 10 by 10 spatial light modulator with 1,000 pixels each. And again, remember, each pixel is a multiplication that you are doing. Obviously, it's very impractical to think of shining one single micro-LED across a 10,000 row of your spatial light modulator. So what we have is an array of micro-LEDs or CMOS sensors to really increase our power budget of the system. And finally, we need some custom optics in order to achieve this row type or column type illumination, as I previously described. So really, to conclude, I have discussed the opportunity that we have by combining the right abstraction, which is QMO, with the right technology, which is commodity optics, and the right algorithm, and all together will drive optimization in the post-Moore's law era. And more broadly, given the advantages and the maturity of optics that I've discussed, I believe the time is ripe for optical computing. So with this, I really would like to thank the team that is actually doing the great work that I've just talked about. I would also encourage you to look at our website. And if you have any comments or questions, feel free to reach us out with the email there. So thank you very much again.